Hey kids, Smath here. Going to do some thermodynamic example calculations for you. We explained this and led us up to this equation that we have right at the top here. Delta H equals MC delta T. That's just a mathematical way of saying the enthalpy, the heat, is equal to the mass times the specific heat times the change in temperature. Now, we did define that change in temperature as well, that we need to understand this is always going to be TF minus TI. Many of you guys are going on, you're going to take physics next year, and that's just going to be, that change in always ends up being the difference between the final minus the initial. Okay, so let's look at this first one. We want to know how much energy in joules is required to raise 525 grams of aluminum from 13 degrees up to 47.8, knowing that our specific heat of aluminum was 0.89 joules per gram degree Celsius. We were given this, it's in the problem. So we have 1, 2, 3, 4 variables, and we are always going to be given 3 of them. So let's take a look at what we have. We have 525 grams. All right, that's my mass, M. The specific heat is 0.89, and the temperature, final minus initial. Multiply those together, I'm going to get 16,000 joules. I told you in the last video, joules are very small. So if we can number this big, it's polite to put it into kilojoules, 16.3 kilojoules, or 1.63 times 10 to the third joules. Either one of those two. But you don't have to. Just be aware, these are pretty interconvertible. What about our second one? So this one, the first one, I'm sorry, before we move on, the first one was how much energy? Calculate delta H. So our variable, I told you it was a 4-variable equation. The variable we were solving for was delta H. What about our second one? We have 193 joules of energy added to 50 grams of copper, and the temperature rose from 25 to 35. Calculate the specific heat. So now our variable, I'm shading it in yellow, our variable is going to be C. So now let's take a look at what we have. We've got 193 joules of energy. That's H. There's 193 joules. Is equal to the mass, 50 grams. Specific heat's what we're solving for. And the temperature went from 25 to 35. So my delta T is going to be 35, final minus initial. And if I just punch this in, a lot of you guys are going to end solve that. That's fine with me. All right. If not, just take 193 divided by 50 times 10. 193 divided by 500, you're going to get 0.386. Specific heats of metals are generally below 1. In the first problem we did, the specific heat of aluminum, 0.89, that's one of the higher specific heats. It's pretty hard to heat aluminum. Copper, really easy to heat. So you see a lot of frying pans and pots and pans that are made of copper. How come? Because it has a very low specific heat. It's very easy to heat up, makes for good cooking surface. Now, what about 3? 3 says, what mass of water could be heated? So now we have not a metal, but we're heating up a certain amount of water. Could be heated from 10 to 25 if 5.15 kilojoules was added. So in this case, what mass, the variable we're solving for, I'm shading it in yellow, is our mass. That's what we're solving for. We started out with 5.15 kilojoules. Just slide that decimal over 3. I got 5150 joules is equal to M. C of water is 4.18. That was given in the problem right here for you. Okay. And the temperature change was 25 minus 10, a 15-degree change in temperature. Plug that into your calculator, let Texas Instruments do all the lifting. We could heat up 82 grams of water. That's kind of a weird type of problem. We don't go sitting around saying, hey, I got this 5 kilojoules of energy. What could I do with it? That's not really the usual. The usual is much more before where we're identifying substance, like problem 2. We're identifying a substance from its specific heat, or we said, hey, we heated up this substance. How much energy did it take? Like example number 1. Now, example 4 is kind of a lab scenario. We're actually going to do this lab virtually. I'm going to do it, share it with you guys on video next week. Okay. In a calorimetry experiment, a student placed 25 grams of iron at 98 degrees into 70 grams of water at 23 degrees. What's the temperature of the system? And they gave us these specific heats. Well, now we've got a fair amount of layout to do for this. Here's what's happening. Imagine a cup. It's got some water in it. That water is 23 degrees and there's 70 grams of it and it's water. So we know that the specific heat of it, C is equal to 4.18. We're going to take a chunk of hot iron and put it into that water. Now that iron had a mass of 25 grams and its specific heat was 0.45 joules per gram degree Celsius. And it started out at 98 degrees Celsius. Here's the deal. What the question really should read is, what was the final temperature of the system? Once the system reached equilibrium, these are both going to reach the same temperature. What's going to happen is, throw a piece of hot metal into water. What's going to happen? The metal's going to cool off and the water's going to warm up, and eventually they're going to reach the same temperature. Okay, now here's the deal. We said the law of thermodynamics, we can't lose any joules. And we also said that energy always flows from high to low. So let's take a look at that. In that case, the iron, 25, so basically the delta H of the iron is equal to the delta H of the water. The iron was hot. It's going to lose energy. The water was cool. It's going to gain energy. So if that's the case, what we've got is negative MC delta T of the iron is equal to positive MC delta T of the water. Now this one's going to take a little bit of work on our calculators. This is going to be negative MC TF minus TI equal to positive MC TF minus TI. And here's the deal, kids. This TF and this TF, they're going to be the same. That this iron and this water is going to reach the same temperature. So let's plug in some numbers, see if we can get an answer that makes some sense. The iron was 25 grams and the specific heat was 0.45 joules per gram Celsius. TF minus 98 degrees is equal to the mass of the water, which in this case was 70 grams, the specific heat 418 joules per gram Celsius, and TF minus 23 degrees. if I plug this all in my calculator, now this one I'm going to let NSolve do the work on, because this is, you could do it algebraically, but you got a little bit of a headache. So we're going to menu 3-1 this and say that negative 25 times 0.45 times parentheses x minus 98 equals, now it's positive, 70 times 4.18 times parentheses x minus 23 comma x, and I've got an answer that's 25.8. My TF equals 25.8 degrees Celsius. As long as that temperature is somewhere between the starting temperature of the water, 23, and the beginning temperature of the iron, 98, we're okay. If we did this problem and we ended up with a temperature that's below 23, it probably means that we forgot this negative sign on the iron side of things. And we just need to be careful of that. But if you set this up and plug it into your calculator, the water's going to warm up and the iron's going to cool down, and we can calculate the final temperature of a system. I look forward to doing this one in video lab for you guys. But I'm Smath. This gives you 4 nice calculations of thermocalcs, and I hope this video helped you.